Today we are examining how inferior coke, not as a theory but as a measured charged material, systematically destroy the large scale blast furnace stability. Now the data comes from a real industrial experiment, the 2011 TKSE trial on blast furnace number 2. So this is a not just simulation, this is a forensic autopsy of the failure, and which in a subsequent slides we are going to share. So let's begin with the macro context and the experimental design. The global market index shows 4.2% stress. Supply chains were already tight, but the real story is here. The TKSE blast furnace number 2 volume 4769 cubic meter ran an 8-week trial from November 7 to December 31, 2011. The catalyst, the KBS coking plant deliberately increased petroleum coke share by up to 20%, that is 350,000 ton of quality reduced coke were charged. 350,000 of this quantity. So 5-week reference period in October gave the baseline. Furnace stability started at 98%. That number didn't hold. What exactly do we mean by inferior coke? The next slide defines it. So inferior coke is not just lower strength, it is a systemic poison. For this trial, the critical change was a reduction in coke strength after reaction, that is CSR. Alongside that, the coke reactivity index CRI rose. Lower CSR means the coke disintegrate under thermal and mechanical load inside the blast furnace, as it is evident to all blast furnace operators. Higher CRI means it reacts faster with CO2, accelerating degradation, or we can say this solution loss or gasification. When we charge when you charge 350,000 ton of this material, you are not reducing quality gradually. You are flipping a switch on instability. So the first place, the furnace signals distress in the top area. Now let us look into all those deviation and deformation that started coming from segment wise. Now as far the top area is concerned, at the top of the furnace, gas permeability collapse. The immediate symptom were reflected in terms of more dust generation, nearly tripled. Valuable ferrous material that should have stayed inside was blown out of the furnace, and there also gets reflected in terms of dust catcher dust. So this is not just inefficiency, this is active material loss. Every kilogram of dust is a replication, or it is a reflecting the loss of production. Now let's look at the specific gas dynamics and what the number tells. Gas utilization, which are the prime index, that is the most concrete indicator which can signify the efficiency of the furnace. So it has here dropped more than 1 full percentage point from 49.7 to 48.7%. But the real problem was not just the drop, it was the erratic distribution also. Top gas temperature rose up to 100 degrees centigrade, that is wasted energy, and the sludge generation spiked. The furnace was no longer reducing iron efficiently, it was venting its performance out of the top. So the instability didn't stay at the top, it moved down into the shaft and wash also. Now, if you look into this slide shows two opposing thermal anomalies. In the shaft, cooling circuit K1 through K3 experience severe temperature spikes, exceeding design limits and which are detrimental for any coolers because they are limited by the specific heat load capacity up to their routine scale and the maximum limit that they can tolerate. Now, erratic gas flow were forced to the outer wall. In the Bosch, paradoxically, cooling circuit case showed a massive drop in heat loss. As far the diagnosis is concerned, that result into thick obstructive scaffold freezing to the wall. That scaffolding causes severe aerodynamic instability rather, frequent furnace slippage and channeling. So, one furnace, two opposite thermal failures started visible, but the root cause remains the same. Now, the next symptom visible to every operator at tier level, and these were very significant. At the tier level, the instability becomes visible. Flame temperature becomes very uneven. Some tiers run hot, other runs cold. The gas distribution is no longer under control. The furnace is now reacting, not responding. And that leads to the most dangerous condition, that is about the pressure runway. So once gas distribution breakdown, pressure control breakdown, operator lose the ability to maintain stable blast furnace condition, every adjustment becomes a gamble. Now the now the results as far is concerned, we call the mm, total asymmetric of the furnace. Despite erratic changes to burden distribution, pressure repeatedly breached the 1.8 bar maximum limit to prevent catastrophic failure. A twin blowback or a shell breach, a nominal blast volume had continuously slashed. That is not a control action. That is basically a survival. That is basically a survival questions on survival way out. And this all resulted into a tremendous metal production loss. The furnace was not responding, it was being suffocated by its own coke. So, to understand why this happens, we have to separate immediate impact from the delayed ones. The, the mechanics of the failure uh, which are in which the immediate and delayed impacts is compared. Some effects of inferior coke show up in hours, dust generation like temperature spike, pressure swing, but the most dangerous effects are the delayed. They hide inside the furnace for days before destroying it from the bottom up. Understanding that delay is the key to understanding this entire trial transition. And here is the mechanical framework of failure. 3 points. The framework. First, the framework, that is coke in the hearth act as a critical physical framework for the liquid iron drainage and upward gas distribution. Without a strong coke, there is no structure. Second, the 12-day delay. It takes roughly 12 days for the furnace to mechanically cycle out the old, a strong reference coke and fully replace it with the degraded trial coke at the bottom. Third, the collapse. Once the poor CSR coke enters the dead man, it crushes into powder under extreme thermal and mechanical load. The physical framework disintegrates. Flow of hot metal and gas becomes permanently throttled. The furnace doesn't die quickly, it dies from the inside over 2 weeks. We have evidence from the autopsy. Tier number 15, core drilled on December 24, 2011. On December 24, 2011, the team drilled into Tier 15. What was they found was not coke, it was crushed fines, totally powder. The dead man had turned into packed bed of debris with no permeability. This is not a theory of degradation, this is physical evidence. The inferior coke didn't weaken, it disintegrated. So, what was the true cost? Let's synthesize. The true cost of inferior coke is not measured in the price per ton, it is measured in operational destruction. Uncontrollable pressure drop constantly exceeding 1.8 bar, severe slipping and channeling, highly erratic gas utilization, and on the material side, 500 ton of non-sealable rock slag sand wasted. No furnace can survive this combination. The trial proved that CSR and CRI are not laboratory curiosities. They are operational lifelines. First, uh, that is our final slide, the conclusion every operator and plant manager must take away. So, the 2011 TKSE experiment was not a failure of operation, it was a failure of coke quality tolerated too long. Inferior coke creates a cascade. Top area dust loss, shaft and boss scaffolding, pressure asymmetric condition, and finally deadman collapse. The 12-day delay is the trap. By the time the furnace shows bottom level symptom, the damage is already irreversible without a complete shutdown. The lesson is simple. Coke quality is not a specification, it is the foundation of stability. Compromise it and the entire system becomes unstable, not in weeks but in hours.